All right, I'm going to make another electricity lecture, this time going more in depth into Coulomb's law. We'll also talk about Ohm's law and things like voltage or potential, current and resistance and resistivity, or resistivity. And that's about it. So let's start with Coulomb's law. We can define the electric force similar to with what we did with gravitational. If you remember, for gravitational, we said Fg equals G m1 m2 over the distance center to center squared. This time we're going to have two charges, Q1 and Q2, and they're going to be separated by a distance r. And instead of G, we're going to be using something called the electrostatic constant. So let's go ahead and write that out. It's going to be K, this will be a lowercase k, K Q1 Q2 over R squared. We're going to use lowercase q's here, although we did say that sometimes charge can be expressed as an uppercase q. So this is going to be the electrostatic constant. And if you remember back to for gravitational constant, universal gravitational constant, this was a very small number, 6.67 times 10 to the negative 11th. This is going to be a very large number. This is going to be 8.99 times 10 to the 9th. And so a much more powerful force, because this constant is 20 powers of 10 larger. Q1 is going to be the charge one in coulombs. These are going to be particle charges. And this is going to be charge 2. And in coulombs, units here, capital C we said is coulombs. I'll just write coulombs. Maybe I'll put a parenthesis around it. And then R is the distance from center to center squared. So distance from center to center. Notice it's not the radius. Okay, so very similar to what we had last time for force gravitational. Okay. Now you might say, well, what's different here, right? Force gravity only attracts, but force electric could attract or repel. So when we solve this equation, we really like to use absolute value signs here. And why is this? Because the force can sometimes have a direction, maybe left or right, and that's positive or negative, or up or down. And that can get confusing if you say that an attractive force is negative and a positive force is repelling, right? So we're going to keep positive and negative for up and down and left and right, and just use magnitudes here. So meaning that if this is a positive and a negative force, then when we're done and we get a number here, we can just say, well, the answer is obviously going to be attractive. Or if this is a positive and positive, or a negative and negative, then the force is going to be repelling, right? So the electric, and I better mention this too, the units on force electric are no different than for any other force. So we would say units of newtons here. Okay. But anyways, yeah, just as a quick reminder then from last time, that positive, or let me see, or negative, negative, the force repels. So like charges repel, and positive, negative, opposites attract. And just as a reminder there. Okay, so let's go ahead and look at some examples. I'm going to do them right from the homework assignment, which I have over here. And then we'll move on to the next part of the lecture. So for the homework assignment, you're going to be given this worksheet right here. It has a front and a back. And on the front, it's kind of conceptual. And on the back, it's more plugging in and using your calculator. So more quantitative on the back. But the conceptual side, what they're going to do is it's going to be very similar to last time in that they're going to modify the situation, right? So for instance, the first one says two charged objects have a repulsive force of 0.08 newtons. We're gonna not worry about the 0.08. We're just gonna say that they have a repulsive force or a force of F, right? And we won't even worry about repulsive or attractive. It looks like maybe a couple are attractive somewhere along the way, but we're not even gonna worry about that right now either. So it says two charged objects have a repulsive force of 0.08 newtons. So we're just going to call that force F, right? And it says if the charge of one of the objects is doubled, what is the new force? So our equation, which I like to write down just to keep it up on top, just as a reminder, force electric is equal to K Q1 Q2 over R squared, right? And and we have a force here that's equal to F. So the idea is that anytime we see just this, and this should sound familiar because we did the same thing for the gravitational force, that this quantity right here is equal to F. And then we're going to change something about this, right? And this, all we're going to focus on is the factor of change. It says two charged objects have a repulsive force of F. If the charge of one of the objects is doubled, then what is the new force? So if we double one of these charges, so I'm just going to put a 2 in here somewhere. Maybe I should redraw this just so I can keep this kind of not looking too messy. So I'm saying that if I double one of the charges, right, I can go ahead and rewrite it. And let's just say one of these has a 2 with it, right? Then I can bring that 2 outside, and really that's all that's changed, right? That what I left behind here is equal to F. Right? Okay, so this is F right here. So my answer would be 2F. Now you might say, well, what about that 0.08 that you ignored? Well, okay, well, if you really want the answer the way that maybe the worksheet intended more so, then you would just sub in a 0.08 for F and you'd get 0.16 newtons for your final force. But the broader idea and the way this usually shows up in AP physics is something more along this line, that they don't give it a number, they just call it F, and if you double one of the charges, then the new force is twice as strong between the two charges, right? So so by having more charge between two charges, the force of attraction or repulsion, in this case, the repelling force, is twice as strong. And it's a Newton's third law force, so the force on one of the charge is equal and opposite to the force on the other, even though one of the charges has twice the strength for the charge. Okay, so that was number 1, right? Let's go ahead and look at let's go number 3. Hopefully you can see that. So number 3 says two charged objects have a repulsive force of 0.08. So again, we're going to call that F, right? If the distance separating the objects is doubled, then what is the new force? All right, so doubling the charge made the force twice as strong, but if we double the distance, right, then this is going to get weaker because we're moving the two charges further apart. And so, but the question is how much weaker, right? So I'm just going to go ahead and write my force nu is equal to K Q1 Q2 over r squared, and then I'm going to put in what changed, which is this 2. Well, we have to realize that when we double r, we have to square it because of that square there. So I can go ahead and rewrite everything that's left over. So force nu then is equal to K Q1 Q2 over, I can keep those absolute value signs there too if you like. Squaring this, we're going to end up with a 4 down here. Squaring r, we're just going to get r squared. So r squared just like that, and then this 4 right outside of here. So this, if this marker's going to work for me, oh yeah, is going to be equal to F. And I have this 4 on bottom out here. Hopefully this is making sense, because like I said, I know we did this earlier in the year. And we have this 1/4 hanging out in front of F, right? Everything in there is F, so 1/4 F. All right, so this is the idea, right? That force electric is proportional to Q, but it's inversely proportional to R squared. So it wasn't half as strong when we doubled the distance. It was, or I'm sorry, yeah, it wasn't half as strong. It was 1/4 as strong, right? Instead of being 2 times weaker, it was 4 times weaker. It was 1/4 the old force, this new force. All right, so let's do one more. I think this one will be a little more challenging. And let's do number 6. And 6 says, what happens if the distance is halved, right? So we're going to bring the two charges closer together. So if we halve the distance now instead of doubling it, then we would expect it to be stronger, right? Because we're bringing the charges closer together. So we can say here, and I'll try and do it the same way I just did it a second ago, F nu then is equal to K Q1 Q2, nothing changed up there. And then we have this 1/2 on bottom. And I'm using a different color marker here because that's really the focus, right? Is what's different. And so I'm going to square the 1/2. Everyone should remember how to do that, right? 1/2 times 1/2 is equal to 1 times 1. 2 times 2 is equal to 1/4, right? Okay. So coming back over here, then I can go ahead and say that 1/2 times 1/2 is equal to a 1/4 on bottom, and I should have grabbed that other marker to write that. And the rest of this is just going to be F, right? So I'll rewrite it really quick, but yeah, everything right here is just F. We have to be careful here not to say 1/4 F, because right, we have a fraction on the bottom of our fraction, and so really there's a 1 up here. So you can think of it as how many times does a 4th go into 1, right? That's one way to think of it. And you would say 4 times, so the answer would be 4F. The other way is you're going to take this 1/4 and you're going to multiply by the reciprocal, right? So you're going to flip it upside down. The reciprocal of 1/4 is 4 over 1, so you're going to multiply by 4 over 1. So this 4 gets to go up to the top, and this 1 gets to stay on the bottom. I think there's some kind of like keep, change, flip or something, but yeah, I forget how to do that. So anyways, you're going to get 4F. So 4F is going to be your answer there for F nu. All right, and that was number 6, I believe. So I can go ahead and write that right there. Okay. On the back, there was one I wanted to look at, and like I said, this is more the calculator side, the calculator check. We'll look at number 12. Well, I probably won't have you do all the problems on the back. I guess if you want to, you can. It doesn't hurt, and they're great problems. But yeah, we'll see. So let's look at number 12. So number 12 says calculate the electrical force in newtons exerted between a 22-gram balloon with a charge of negative 2.6 microcoulombs. All right, I'm gonna start drawing this because otherwise I'm gonna forget what the problem said. So I have a balloon here. We'll call this charge 1, and it's gonna equal negative 2.6 microcoulombs, and it has a mass of 22 kilograms, or sorry, 22 kilograms, 22 grams. I don't remember seeing mass anywhere in our force electric calculations, so it's probably not going to matter, right? And it says, and a wool sweater. Oh. Skills right there. A wool sweater with a charge of, we'll call this Q2, with a charge of positive 3.8 microcoulombs. Okay. And a separation distance of 0.75 center to center meters. So 75 centimeters, right? Okay. And then they give us a hint here. They say that 1 Coulomb is equal to 10 to the 6th microcoulombs. Okay, but we don't have anywhere near 1 Coulomb, right? We have a much smaller amount of charge. We have 2.6 microcoulombs. So you can probably see where I'm going with that, right? Because R checks out as being okay. It's in meters. Here, this being in microcoulombs just isn't going to work, right? We can make the change pretty easily. We can say that 2.6 microcoulombs is equal to, or negative 2.6 is equal to negative 2.6 times 10 to the negative 6 coulombs. Because 1 Coulomb is a lot of microcoulombs, but we only have a tiny amount of microcoulombs, so we have a very tiny amount of coulombs. And 3.8 microcoulombs is equal to, or positive, is equal to positive 3.8 times 10 to the negative 6, again, because it's a tiny amount, right? This negative in the exponent doesn't tell us a positive or negative number. It tells us a large or small number, which is a small number for right here. Now you might say, well, how did I do that? How did I know that? Just, moving my, like we talked about, moving from the base unit, which was coulombs. I think we have, if we remember right, or if I remember, deci, centi, milli, and then we had space, micro, and we were starting in micro, right? So I can go ahead and show you this. So for the first one, I had negative 2.6, and then I was starting at micro. So I'm going to start here and move my decimal 1, 2, 3, 4, 5, 6 to the left. So my decimal down here is going to go 1, 2, 3, 4, 5, 6 to the left like that. So the answer is going to be put a 0 in all the values, 0.00000, and that negative sign still there, 2.6. So if I rewrite that, it's negative 0.12345 and then 2.6. So I called this 2.6, negative 2.6 times 10 to the negative 6, right? Coulombs. But you're free to just call it this, right? 0.3 zeros, 2 more zeros, 2.6 coulombs, and that's right. Either way. And so by that same logic, then 3.8 would be, if I do that one more time, starting at 3.8 microcoulombs, moving it from micro all the way over to coulombs, 1, 2, 3, 4, 5, 6, 6 to the left, 1, 2, 3, 4, 5, 6. And you can see, once again, I'm going to tack on 5 zeros, 2 there, and then 3, 8. So this would equal 0.00000038 coulombs, or 3.8 times 10 to the negative 6 coulombs. All right, so that's where I got those two charges from. Okay, so when we plug those into the actual Coulomb's law, we can see it looks like this, right? Force electric is equal to K, which is 8.99 times 10 to the ninth, a very large number. Q1, which is the negative 2.6 times 10 to the negative 6 coulombs. Q2, which is 3.8 times 10 to the negative 6 coulombs, divided by 0.75 meters squared. And now it becomes a calculator problem. So I like to then crunch the top, crunch the bottom. Let's see if I have my calculator. And give this one a shot. I like to put all these in using parentheses, so that 8.99 EE times 10 to the ninth. You got that right there, a large number, times that the charge for the balloon, parenthesis again, negative 2.6 times 10 to the negative 6th. All right, get a little smaller from that. And then once again, multiplying by another small number, but this time, and we did say, and notice I put the negative sign in. I really don't want to use the negative sign. I told you guys that I was going to keep that absolute valued, and I didn't. All right, like that. Okay. Well, all right. Let me, I guess I could have just got rid of that. Let me start over. Times, we're going to go 2.6, right? Ignore the negative sign. We'll know at the end it's got to be an attractive force. 2.6 times 10 to the negative 6th. Okay. And then times 3.8 times 10 to the negative 6th. Okay, even smaller. And then we're going to divide by whatever's on bottom. And what I like to do sometimes here is just write this down. So this is the 0.08881212. And then I just want to know what's on bottom there. 0.75 squared. 0.5625. So that's what I have there, right? And I can go ahead and type that in. Get about 0.158. And units here, this is a force, so units here should be newtons. And we would say, since this is a negative and a positive, right, would be attractive. All right, I think that was all the question was asking. Calculate the electric force in newtons. Yeah, so PSYW, please show your work. Okay, all right, let's move on. So from there, what I want to talk about is a few different things. We have another law that I want to get into here instead of Coulomb's law, which is Ohm's law. So Ohm's law, if we write this down, and we're going to come back to it, is V equals IR. And I want to talk about what all these constants mean, right? And this is not moment of inertia, by the way. So we're going to have an I, capital I, that means something else. Okay, so the first thing I want to do is kind of draw another comparison to potential energy. And and I think you remember your formula for gravitational potential energy. So we'll hold off on talking about Ohm's law immediately. And remember that PE equals mgh. Now, if this is the case, and let's say you're out at the tennis courts, and out at the tennis courts there is a set of bleachers. If you sit on these bleachers, they're not very tall, right? But we're going to make these ones a little taller just to make our example easier. We'll say the first bleacher is 1 meter off the ground. The second bleacher is 2 meters off the ground. All right, these are quite a bit higher than the ones at the tennis courts. And the third bleacher is 3 meters off the ground, right? Okay. Well, we know that if we take a tennis ball and had a green marker, maybe this one will work, and we were going to drop it from right here, right? And we're going to drop the same tennis ball from right here. And maybe we did the same thing in the middle too, if we like. But if we just look at the ends, right, and drop the tennis ball from here and drop it from here, which one has more potential energy? And right away, you would all say, well, this one has the greater height, so therefore a greater height would be a greater potential energy. It makes perfect sense. The mass of the tennis ball is the same. The planet is the same. And you're right. But let's say we replaced the tennis ball with a apple. Or even maybe something different. Yeah, we'll do an apple. Okay, I'll try and draw an apple. This probably isn't going to go. All right, an apple, right? And we put the apple here, and we put the apple here. Which apple has more potential energy? The apple when it's here or here? And once again, you would say this one, right? Because it has the greater height. All right, well, what if we took, say, instead of an apple, we took something with even heavier mass, maybe a tennis racket. Right? That's a tennis racket. Okay. And we put the tennis racket at the same height over here. Hopefully you can see that. Okay. And we did the same thing, right? And which one would have more potential energy? And once again, you would say right here. So what I can say then about maybe this height or this height, I could call it a potential line, right? That if you are at this height right here, that we can say this is a potential line. And it's different from, say, this height right here. And what I'm trying to get at here is that if you place a mass at this height, at this potential line, it will have more potential. It will have more potential to create potential energy. Does everybody agree with that? I think you should, right? And if you place a mass at this height, right? I don't care if you're at, by the bleacher or wherever, but at this height from the ground, then it will have less potential to create potential energy. So what is potential then? Potential is this right here, is G times H, right? G times H is this idea that there's something called potential, and it's some number, right? It's 9.81 times 3. It's 9.81 times 1. So I guess the potential here would be about 10, right? 9.81 times 1. And 9.81 times 3 is about 30. So the potential here at this potential line would be 30. And the potential here at this potential line would be 10. And the potential here at this potential line of 2 meters would be 20. Okay. So now we're given it a number, and we're given a quantity to this idea called potential. And why am I bringing this up, right? Well, let's think about electricity now. So for electricity, there is something called potential energy electric, right? I mean, if a gravitational force is going to create potential energy of gravity, then why can't an electric force create potential energy of electricity, right, for a force electric? And it can. And this can be equal to Q times, well, G, if you remember, I gave G another name. I called it a gravitational field. And instead of a gravitational field, we'll call this an electric field. I'll give it a little vector symbol because it is a vector, n times a distance. So I have QED. So this idea that instead of putting a, and maybe I should just mention, remind us what a gravitational field is. There's two ideas of forces, right? One is that you have two particles that pull on each other, and that's a particle model, right? If mass 1 or if charge 1 exerts a force on charge 2, they pull on each other with a force electricity. The second model would be a little different, would be a field model. And a field model is where you have one charge, right, that changes the space around it, right? It changes the space right here. It changes the space right here. And in everywhere where the space is changed, there is a field. And the field exerts a force on a charge when it's placed there, right? And if it's further away, it exerts less of a force. And further away, less still. That should be smaller than that. You get the idea, right? Though that the field model is going to be where a charge changes the space around it and the field exerts the force. So what I'm saying is this charge is exerting an electric, or is creating an electric field around it, even if there isn't another charge there. Whereas in the particle model, the force came about from the two charges interacting. So different models of looking at a force electric. And the same thing could be true of gravity, right? The Earth and you. And you might say, well, what if I wasn't there? Would the Earth still exert a force? And according to this model, I guess it really wouldn't, right? Because you're not there to experience it. But in this model, it creates a gravitational field, and whether or not there's a mass there to experience it. Obviously, the arrows would point towards the Earth if this was the Earth. Okay, so anyways, coming back to this, if G times H was potential for gravity, then electric field times distance, this is going to be charge, right? Charge is kind of analogous to mass, right? Electric field times distance is going to be potential for electricity. Okay, so mass is lining up to charge. Baby G is lining up to electric field. Let me write that down. So this is E, this is an electric field. And D is distance, kind of lining up to H, right? Okay, and so why talk about potential? Why not just talk about electrical potential energy? And I don't have a great answer for that, but I can explain that that is the normal way we do things with electricity, right? When you go to the store to buy a battery, you don't necessarily buy electric potential energy, right? You buy potential. And what do I mean by that? Well, let's dig a little further here with potential. So potential is also known as voltage. And potential then is the symbol V. And potential has units are volts, which have also, and volts have the symbol V. So let's say you go to the store and buy a 9-volt battery, then you would say that the battery has a voltage of 9 volts. So the potential, let me see if I can make this clearer, or voltage of that battery is 9 volts, is what I'm trying to say. So why do these batteries have a 9-volt potential, or how does that work? What they do is this describes a constant potential between two charges on a battery. So if you buy, let me see, if you buy a 9-volt battery, let me think about that. If you buy a 9-volt battery, I don't normally buy 9 volts. I'm pretty sure a 9-volt looks like this, right? And you have a positive and a negative terminal. What that's saying is there is a potential difference between these 2 points of 9 volts. That a battery will create a constant potential difference of 9 volts between its positive and negative end, and that's what I'm trying to say here. Okay, let's go a little further here. Okay, so what batteries do, and maybe I guess I can draw this really quick. So, because we're going to start drawing circuits here, and this video is getting pretty long. I might have to pause it right here. Okay, so I wanted to cut that off there because the videos get too long. They don't send very well on my email, and I run into problems. So coming back to this, let me write a definition for potential here, because this is a complicated idea. So potential, I'll write this in a way that's kind of complicated too. Potential is then the potential is the potential to create electric potential energy. Right? And so what we're saying there is this battery is going to create a potential difference here. And when we put electrons, or if we put charge on a terminal, if we say we put positive charge on this terminal, it's going to want to use that potential. It's going to experience a force, an electromotive force, to move through the circuit and drop its potential, right? So what we buy with a battery then is kind of like electric potential energy, but it's not quite the same, right? Potential is the potential to create electric potential energy. All right, hopefully that makes a little bit more sense. Let's see it in a circuit, right? So I said last time we would draw a circuit. So let's go ahead and draw the symbol for a battery. And maybe I'll start with just this. So a battery has a longer line than a shorter line, and the longer line is going to be positive. So here, I'm going to draw it 2 ways, and then we'll talk about it. Now, which way is right? Well, they're both right, but I think technically this one is more correct. And why is that? Because a battery, this would be a cell, right? A single cell. And a battery is cells combined. So when we line up 2 cells in the identical way, right, with positive on top, negative on bottom, we'll say, it's arbitrary. I could flip that. You could flip a battery. That then becomes a battery. So anyways, I'm going to usually draw my symbol like this. But I could just as easily do it this way. So maybe for today's lecture we'll stick with this one just to make it simpler, right? Okay, so let's say we have a battery then. Always label your positive and negative terminals, just so you remember, and it's a good habit to get into. We're going to then make a circuit. And we'll have maybe a light bulb right here. And then we'll complete our circuit. We'll close our circuit. Okay, so here's my light bulb. And here I have a circuit. This battery is drawn like this, right, with a positive and a negative end. And what it's like is a charge escalator. So what's going to happen is maybe this is a 9-volt battery, and I'll just go ahead and label that right there. We also call these an EMF source, but a 9-volt battery works just as well. So what we're going to say is when we lift these charges up, they have potential. So if we were going to get a voltmeter and measure the potential right here at that point, it would have a potential of 9 volts, right? And then this charge, because current is directed this way, we'll talk about that in a second, and this charge is going to move here through the bulb, and the bulb's going to have a resistance. Maybe the bulb is a I don't know, I'll just make something up, a 4 ohm resistor. So we'll say R equals 4 ohms. And then this charge is going to keep moving this way, right? All the way back to the battery. And if we measured the voltage here, it would be 0 volts. So what we're seeing is the voltage is spent at the resistor. And so this potential that the battery gave these electrons, it kind of or charge, it kind of is like lifting the charge up and then letting the charge fall, right, and gaining kinetic energy through the circuit, through the copper wire. This is what this is. This is the wire. And then hitting the filament of the bulb, running into the filament, which is a resistor, and causing heat, causing light, causing energy, causing the light bulb to light up. And then the electrons or the charge, I keep saying, I got to clarify which one. This is actually going to be positive charge here we're talking about. The charge then moves on past the bulb and then moves back to here. So a couple things are true there. One is that the charge isn't spent at the bulb, right? And you should, I think we talked about that last time, right? Conservation of charge. Maybe make a note of that. And I'll just remind you that charge is like electrons, right? I'll put a question mark there though. So what is spent at the bulb? Well, look, 9 volts, 9 volts, 9 volts, 9 volts, 0 volts, 0 volts, 0 volts, 0 volts. Chemical reaction, redox reaction, charge escalator, right? The charges are lifted up. It's like there's an escalator giving them energy, lifting them up, and then they run, turn into kinetic energy, hit this, create thermal energy or heat energy, and then they come back here, chemical energy once again lifts them up, and they have electric potential energy or electric potential with 9 volts, and that creates electric potential energy, right? So so you kind of get the idea, right? And that's how it works. So let's talk about a few more of these ideas then. So we kind of got potential down, right? There's this idea that potential is the potential to create electric potential energy. Yeah, so this battery has potential, a potential difference between its negative and positive ends, a constant difference that it can create. And these charges have electric potential energy, which turns into kinetic energy as it falls, or you can think of it falling here, and being lifted up here to create the electric potential energy or the potential, and then electric potential energy being turned into kinetic, being turned into thermal, being turned into chemical, turned into electric potential or electric potential energy, yeah, and so on. Okay. All right, let's go ahead and move on to the next one, which is current. And we'll come back to that circuit here eventually. All right, so current is capital I. Current is the amount of charge per second. Amount of charge that moves through the wire per second. And furthermore, it's not just the amount of charge, it's the amount of positive charge. And that's important to remember. Now you might say, well, I thought electricity was all about electrons and electrons are negative, but the thing here is they didn't know when they were first discovering electricity, they didn't know that charge was negative. They didn't know electrons were what was moving around. So they referred to charge as always being positive, and current as being the amount of positive charge that moves through the wire per second. And so we run into this idea with something called conventional current. So conventional current is positive charge, and is always positive charge moving through a circuit. So whereas current moves this way, positive charge moves this way, what's really happening, even though they didn't know this, right, is that the electrons are moving this way, right? But they didn't know that. So why do we care, or why do we bring it up? Because we always draw current as the way positive charge would move. So our current is always going to point this like this green arrow, even though what's really happening is more like this maroon arrow. So whenever they ask you to draw current, make sure you draw it the way that positive charge would move. Just like that. Okay. So coming back to that, what we were writing there. So the amount of positive charge that moves through the wire per second. If you remember then, the symbol for charge was Q. If it's per second, we're saying that I then is equal to Q over T, where this is charge in coulombs. Whoops. And this is time in seconds. And this is current in amperes. And the symbol for amperes is capital A. All right. And I guess one more thing before we move on to resistance, just to say that then the positive charge here, as it moves through, we said charge isn't spent at the bulb, but that also means, or current isn't spent at the bulb, but also electrons aren't spent at the bulb, right? The light bulb isn't eating electrons or destroying electrons. Come on, give me a break, right? Charge is matter, right? And matter isn't destroyed. Matter is conserved. Charge is conserved. Electrons are conserved. Current is electrons per second, or it's actually technically charge per second. And therefore, if charge isn't spent, current isn't spent. So current is always conserved, and that's something to remember, right? So I can write that down here. Current is always conserved. All right, We'll talk more about that with Kirchhoff's laws, hopefully eventually here. Okay, so coming back then to resistance. Maybe I'll get a new slide here, a new piece of paper for resistance. Resistance is represented by the symbol R. And a good definition for resistance is a measure of how hard it is to push charge through the wire. All right, so whereas current was the amount of positive charge per second through the wire, resistance is the measure of how hard it is to push charge through the wire. Units here are equal to ohms. Ohms also have a symbol of, looks like that, like an upside down horseshoe. This is the Greek letter uppercase omega. So I'm bringing that up because I think last time we said lowercase omega. I think you all should remember what that was. That was that W, like the script W. And so uppercase omega looks like this. Lowercase omega, this was angular velocity, right? All right, so you really got to know what type of subject you're talking about with these variables, right? Because omega could mean, if it's lowercase, it's angular velocity. If it's uppercase, it means ohms, it means resistance. And then we're seeing that current, I could mean moment of inertia, or it could mean current, capital I. Okay. So coming back to resistance here, I want to talk about how we solve for resistance, or how we maybe things that affect resistance, right? So there's this other equation here, and it looks like this. And it says that resistance, right, and this is going to be in ohms, is equal to resistivity times, and this is the Greek letter, you recognize that one? That's like density, right? So that was rho. It times the length of the wire. I should really just say the length of the resistor, right? Because it might not be a wire. It could be something else. So times the length divided by the area. All right, and so what does that mean, right? What is that saying? Well, if we think about this, right, we're saying that if we stick with a wire for a second, that a longer wire has more resistance. All right, and so if you were say wiring up a speaker system and you wanted some good sound, you would use shorter wires, right? Because these two are proportional, L and R. Area, though, is on the bottom. So as area gets larger, this would be an inverse relationship with resistance. And so we would expect less resistance if we were to buy thicker wires, right? And if you ever go hook up a speaker system, or in your car or at home, the wires that are the best are the thicker wires, because they have less resistance. And finally, we have something called resistivity. And this is saying that the type of material that is in the wires matters, right? This is kind of like mass and dense. This is like mass and density in a way, and not. So for this is a constant based on the material. So whatever material you grab is going to have a resistivity constant that is either going to be small if it's a good conductor, or it's going to be large if it's a poor conductor, right? So we would expect copper to have a very small resistivity constant. And I think, let me see here, if I get my textbook out, and I had a table I wanted to show you guys. It's page 710. If we go to 710, and I hope, see if you can see this. All right, so what I'm trying to say here is the resistivities of different materials are different, right? Obviously. And it's kind of neat here because we see things like the fact that the best conductor, copper, has a tiny resistivity like we predicted. And we can see the difference between pure water, which is actually not as good as something like seawater, right? Which is much smaller. Now, why is that? Because, well, seawater has ions in it, has salt ions in it, right? And it allows it to conduct electricity a lot better. Temperature matters, right? Tungsten at a lower temperature is a better conductor. And that's what we'd expect, because if you think about your cell phones and your computers, as those wires heat up, those copper wires, they're not as good at conductors. A better conductor than copper would be gold. So if you can buy gold wiring, then you got a lot of money, and that would be a great way to get a nice sound if you were trying to build a sound system. Okay, so let me get rid of this. Okay, so before we move on then, I just want to mention, if you were to say, be asked a question where you had to draw or sketch, right? It's really not drawing, we're just kind of sketching the relationship between the resistance and the length of the wire. We would say that we would draw something like this, right? A line like this, where as the length gets longer, the resistance goes up, right? So this would be a proportional relationship between resistance and length, because it's a straight line that goes through the origin. So we call this proportional. You know, we'd say something like R is proportional. That's the proportionality symbol. Kind of looks like alpha. Proportional to length. Okay. And then the other one I want to point out is, what if it was area, right? Maybe I'll write out area. Okay. And we had resistance over here. Now we would say, well, this is an inversely proportional relationship. And this is a good one to know too. It kind of looks like this right here, right? And what we see is that as area gets smaller, resistance gets greater, right? So you get those really thin wires, and they're going to have a ton of resistance. But as your area gets larger and larger, your resistance is going to approach zero, right? And so the resistance is going to be very tiny height, right? So it's going to approach zero as the area of those wires get larger and larger. Okay, so kind of neat there. A way to think about calculating resistance. I don't know. Okay, there you go. Looks a little bit better. Put some kind of box around it. All right. So I guess you could say it this way before we move on to Ohm's law to finish this up. Just remember that resistivity is a characteristic of the material, whereas resistance factors in is it factors in the material type, and its geometry, right? So I think the textbook explains it like, this is like density for matter, and this is like its mass. Yeah, if that works for you. Okay, let's move on and get one last concept here. And that is Ohm's law. Okay, Ohm's law says V equals IR. Voltage. And this is also known as potential, right? Just right, or potential is equal to current. How much charge gets through the wire per second. And then the resistance, the amount of a measure of how hard it is to push the charge through the wire times its resistance, right? How difficult it is for the charge to get through. Okay, and in this relationship could be written three ways, right? We could write it another way: I equals V over R, or we could write it R equals V over I. I tend to just write it one way, and if I need to, I'll move it around. All right, I want to do some examples, and then we'll be done. Okay, so the examples I want to end with are from the Ohm's Law worksheet, which is also part of your homework. And specifically, I want to do number 12 and part of number 18. All right, so 12 gives us two circuits, so circuit A and circuit B. And I'm just going to go ahead and draw them right here. This is a switch symbol right here. And what this means, these two dots, is that you could lift this up, right, like that, and open the circuit here. And if you did that, no current would get through. So it would lower the current of the circuit to 0 and turn it on and off. And so we want the switch closed, and we want the circuit closed so that current can get through. All right. Then we have a light bulb right here. And I forget the resistance on it. This will be circuit A. And then we also have one that looks very similar to that. I'm going to label my positive and negative end of my battery. Same thing here. Positive line is always the longest. I always draw my battery this way, so that way charge is lifted up and has electric potential energy, right? When we give it potential here, because this battery is a 6 volt potential, and so we lift charge up, give it electric potential energy this way, and give it so it has 6 volts of potential, spends all 6 volts here, and then comes back around and then gets lifted up again. So I always draw the positive on top, the negative on bottom, and I talk about the way positive charge would move, even though electrons move the opposite way. All right, anyways, coming down here, 2 batteries this time, and 2 6-volt batteries. So we'll deal with that in a second. And this is going to be circuit B. Once again, a switch right here that is closed, so we don't have to worry about that. Switches don't show up too much on our problems, but light bulbs do, and resistors. Light bulbs are resistors, except they light up, right? And resistors, while their only purpose is to give resistance to the circuit, probably lowering potential and things like that. Okay, so I also want to connect this. I don't know why I didn't do that. All right, so there's gaps here, right, where the battery is. That's what that's saying. So there's really no gap there. That is a battery. And but the symbol involves, we draw it that way because that's where the chemical reaction is happening, right? That's where we go from 0 volts to 6 volts with our redox reaction, and our electrons complete the circuit, right? Batteries can sit for a long time on shelves and stay good, because if the electrons don't run around the circuit to the other end, then the battery can't run its redox reaction. It can't run its chemical reaction, so the chemicals don't run out, right? Eventually, those chemicals are going to run out, and we can't run that reaction anymore, right? And so rechargeable batteries will push the reaction the other way, right? They'll send the reaction back, but eventually the chemicals run out. And those rechargeable batteries oftentimes don't last forever either. So there has to be some degradation there in the chemical reaction. All right. So anyhow, coming to this, what is the total voltage in each circuit? So for 12A, right? For circuit A, and I guess I'll answer this twice. I'll just do it this way, right? I think you can see that. Okay. Yep. Okay. And so this will be 6 volts up here for circuit A, and down here it'll be 12 volts. So we just add them together, right? As long as the batteries are plugged in the same way into the circuit, we can just add them together like that. Part B, how much current would be measured in each circuit if the bulb has a resistance of 6 ohms? All right, so for part B, we want to know I, right? So we know V equals IR, but we also can just rearrange this and say I equals V over R. And so we can say that we would have how much current? Well, we have if the bulb is 6 ohms, so we'd have 6 volts over 6 ohms, which is 1 amp, right? And then for here, for part B, once again, we can say I equals V over R. Hopefully you can see this. I know the lighting's changing in this room. We have, and I usually don't like writing things to the right here, so I'm not going to do that. I'm going to write it underneath. I equals 12 volts over 6 ohms. I say I'm not going to do it, and I still do it. 12 divided by 6 is 2. So 2 amps here in circuit B. And that's when this is a 6 ohm bulb. All right, part C says, well, what if it was a 12 ohm bulb? All right, then part C is fairly simple, right? Up here then, we could say I equals V over R again, which is equal to 6 volts over 12 ohms, which is equal to 0.5 amps. So by doubling the resistance, we halved the current. So obviously a inverse relationship there between current and resistance. Okay, and then down here for part C, I equals 12 volts over 12 ohms, which once again half the current, right? This will be 1 amp. Okay, part D. Is the bulb brighter in circuit A or B, and why? Okay, so we haven't talked about brightness. Brightness is power. So let me write that down. Okay, so what's power? P equals IV is our formula for power. So if for part D, if we want to know which bulb is brighter, we just got to use this formula here and solve. That's actually a more interesting question than just that. But I think I'll talk about power next week a little bit more. So up here, and it doesn't, I don't know if it matters which one we pick, but I'll pick, I don't know, part C was the most recent one. So power then is equal to current, which is 0.5 amps, times the voltage, which is 6 volts, which half of 6 is 3. What do you think the units are in power? Same as it was before for energy. Power is still energy over time, so it's watts. All right. And then down here, we have 1 amp, right? I'll use part C. So P equals IV. We have the 1 amp times the voltage here, which is 12 volts, is equal to 12 watts. So therefore, bulb or circuit B, right? I forgot to draw the B here. We can see then B is brighter. Okay. All right. Hopefully, like I said, that's easy to see with the lighting in here. All right. Good. Let's look at 18. 18 says you have 4 1.5 volt batteries, a 1 ohm bulb, a 2 ohm bulb, a 3 ohm bulb. Draw a circuit you could build to create each of the following currents. There may be more than one possible answer. All right, so we just got to rearrange these differently just to build different currents, and it's kind of a numbers game. If we have 1 amp, well, I guess we should probably look at the relationship, right? We want different currents. What is the relationship here? Well, let's remember Ohm's law, V equals IR. I then is equal to V over R. And so to create for part A, which A asks for, this is 18A, by the way, asks for 1 amp, right? To create 1 amp, we would need the voltage and the resistance to be the same, right? The same number on top and bottom. So, so right away, if I use every battery, that would be 1.5 plus 1.5 is 3, plus 1.5, 4.5, plus another 1.5, 6 volts total, right? And if I add up all the bulbs, because bulbs in series, as long as I put them one after another, add their resistances. So 1 plus 2 plus 3 is 6, would be 6 ohms of resistance. So if I put all the bulbs and all the batteries in the circuit, I should have my total voltage be 6 and my total resistance be 6. And because I would then have 6 volts divided by 6 ohms, I would get 1 amp. All right, so that's how I'm going to build that first circuit, right? Now, that's not the only way. There's other ways, but this is one of them. All right, so we're saying we got, how many batteries? 4 batteries? Ugh, lots of draw. All right. There's 2 so far. These are each 1.5 volts. Hopefully you can see that. It's always about this time of day when the sunlight starts coming in through these windows at a different angle, and it gets harder to make a physics video. Okay, there's 1 bulb. I think we said we were going to use 3 bulbs. Yeah, 1, 2, and a 3. Okay. Bulbs aren't perfect. All right, so it's starting to look like that right there, right? And I'm going to go ahead and label these. I'll say this is the 1 ohm bulb, this is the 2 ohm bulb, this is the 3 ohm bulb. Does it matter? Well, kind of. Yeah, I mean, not the order, but they are going to use up different amounts of this potential, right? And they're all going to get the same current because they're in series. Why? Because there's something called Kirchhoff's junction law, which says that the current in equals the current out. So whatever this current is, well, we already said it's going to be 1 amp. 1 amp is going to go in, 1 amp is going to come out. 1 amp goes into this bulb, 1 amp comes out. And I can go ahead and label the direction of current. Direction positive charge would move would be clockwise in this case because of how I drew my circuit. And usually it's going to be clockwise because I tend to always draw my circuit this way. All right, so there it is. If you were wondering, well, how much voltage did you spend at each bulb? How would you calculate that? You would use Ohm's law, right? V1 equals I1 times R1. V2, I'm calling this bulb 2, is equal to I2 times R2. V3 is equal to I3 times R3. So here, for this bulb right here, right? It's easier for this first bulb, we can see then that the voltage you would spend, or the potential, would be if this is equal to 1 amp, because we already proved that, right? 6 volts divided by 6 ohms, that this would be 1 amp times 1 ohm. Which is equal to 1 volt. Okay, so we spend 1 volt at that bulb. This one would be 1 amp times 2 ohms. And this one, which would be 2 volts. Right? Okay, hopefully you can see that. And then this third one would be 1 amp times 3 ohms, or 3 volts. So that's interesting, because what that shows is that V1 plus V2 plus V3 is equal to V total, which is 6 volts. Okay, that's kind of where we're going to go next week. All right, so what if you wanted to build, this is part A, right? What about for part D? It says build a circuit with 6 amps, right? Well, how would you get a number 6 here? What would I have to change about this? 6 divided by 6 is 1. What if I wanted to stay 6 over here? 6 divided by what? Let's say 1, right? So if I then got rid of the 2 ohm and the 3 ohm resistor and kept all of these batteries, then I should be able to solve part D, right? So part D would probably look like this. All those annoying batteries again. Plus, minus, plus, minus. Right? And then over here, just 1 bulb. And current, once again, this direction right here. Clockwise, positive charge would be lifted up, sent around. And this would be our 1, 2, or 3. We said this is going to be the 1 ohm bulb. And then finally, if we want to solve for current of this circuit, right, these all add together create 6. I is equal to V over R, because V equals IR. And we could say then I is equal to 6 volts over 1 ohm, which is equal to 6 amps. Not to be confused with an amplifier like you might have in your car. That makes the amplitude of the wave larger. That deals with energy. It amplifies the sound wave, whereas this is ampere. So 2 different kinds of amps: a car amp versus a amp for a circuit, which is the amount of charge that moves per second through the circuit. All right, hopefully that made sense. And if not, ask me some questions, give me some emails, and hopefully you're having a good week. And I will talk to you later.